Hello, everybody, and welcome back to Business Statistics Online. We keep talking about Chapter 3 this week, so in this video, I will talk to you about two topics: coefficient of variation and applications using z-scores. So the first tab that we're going to use is days on the market. So this represents the data for 100 properties that were on the market for a particular number of days before they were sold. Okay, and we want to generate two random samples of size 35 and then compute the coefficient of variation. All right, so how do we do this? You already know how to compute or how to generate your random sample. We're going to go to data analysis, sampling, press OK, input range, so highlight your data here. Okay, we need to use random sample of size 35, and the output range is where you would like to store your sample, so over here is good. Okay, and here's my first sample. I'm gonna go ahead and do this again. So going back to data analysis. Everything is already set up for me. The only thing that I need to change is the output range. So let's put this one here. Okay. And of course, as you guys are doing this, if you're watching the video and also producing the samples, you will most likely get very different samples, and that's okay. All right. So now let's go ahead and compute the mean and standard deviation for each of the samples. STDEV S stands for sample. Of our first sample, we're going to highlight this, close parentheses, and this is what we get. So the standard deviation for the first sample is 34.5 days. Okay, what about the mean? That's average of my sample is 83.74. So these are the characteristics of my sample 1. Okay, let's see what we get for the second sample. So equals standard deviation dot s, and we have these values right here. We get 54, which is a lot different than 34, right? Almost 55. What about the mean? The mean of this sample is, let's see what we get here, 88. So whenever we have means that are different, standard deviation is not the best way to compare our samples for consistency. In this case, we would like to look at the coefficient of variation, and the one that's lower will have a more consistent set of data. Okay, so how do we compute it? Coefficient of variation is standard deviation divided by the mean times 100, right? So times 100. Okay, so this is 41%. And what about the second one? So here we have standard deviation divided by mean times 100. Okay, here we have 62% roughly, right? Here is 41. So in this case, yes, we have more consistency with in sample 1. So the standard deviation is lower, and so is the coefficient of variation. That's not always the case. Sometimes you will have standard deviation higher, but the coefficient of variation lower. That's why when you have different means, this is the better characteristic of consistency of the data, right? So how consistency between the two data sets. So the lower one represents the more consistent set of data. Okay, so that's what we have here. All right, let's take a look at the Z-scores application problem. Okay, we have the following situation. Tina scored an 88 on her test, right? And she was bragging to her best friend that she's done so well. Now, she said that her class average was 81 with a standard deviation of 6 points. So she did better than average of her class, and that's true. Her best friend, Anna, was disappointed because she only scored 84, but the average in her class was 76 with a standard deviation of 5. So the question is, who really did better on that test relative to their class? Okay, so whenever you have an application problem like this, I think it's a good idea to write out what you have as far as numbers, right? Just kind of organize all your numbers in a nice way. So Tina scored, what did she score? She scored an 88, okay? And her class average was 81 with a standard deviation of 6 points. So did Tina do better than the average? Yes, she did. Okay, 88 is higher than 81. What about Anna's situation? Anna scored 84 with the mean being 76 and the standard deviation being 5. Okay, did Anna also scored better than the average in her class? The answer is yes, but if you take a look, Anna's scores is actually smaller, right? Her raw score is lower than Tina's, and that's why she was upset. But they're in two different classes, they're in two different courses, so the test might be different, right? So whenever you have a situation like this where raw scores cannot really be compared, but rather we can compare the value relative to the rest of the group in this class, then we're going to be using Z-scores. Okay, so how do we compute Z-scores? Remember what a Z-score is. Z-score is how many standard deviations is your score away from the mean. Okay, so what we're going to do is the following: test score minus the mean divide by the standard deviation, right? Okay, so the Z-score for Tina is 1.16 repeating, right? So she is 1.17 standard deviations above the mean. Okay, so yes, she did better. Her Z-score is positive. Okay, what about Anna? We're gonna do the same thing. Her test score minus the class mean divide by the standard deviation. Now Anna did 1.6 standard deviations. She actually did better. Her Z-score is further away from the mean. Okay, so relative to her class, Anna actually is the one who did better. Okay, now you might say, do I need to remember this formula? Well, it's a good idea to remember it, but there's also a command. The command is standardize, right? So standardize, and you just need to remember in which order we need to put stuff in. Test score, comma, mean, comma, standard deviation. It does all the computations for you, but I think it's simple enough to remember this formula. Same thing here. Let's do standardize. Okay. X is the value that we got. Standard deviation first and then second is mean. Standard deviation is last, right? Okay, 1.6. So what is the conclusion? Okay, since Anna's score is higher than Tina's, she did better on her test relative to her class. so she shouldn't be upset. She should actually be pretty happy about her grade because maybe her test was harder and she still did better. Okay, looks like it because the average is smaller, right? Okay, so we can do this comparison when we know that the data is approximately distributed. That's something that we're going to talk more once we talk about normal distribution. But test scores in general are normally distributed. That's why we can do this type of stuff. Okay, all right, thank you for watching.